So I've been, I would like to introduce myself. I've been in the industry since 2002. Started as a QC engineer in Mitsubishi HB board. So normally when all the relays, breaker, CT will be dispatched in production for assembly, we normally do the testing for them. So pretty much all, and then do some kind of pre-commissioning on site and commissioning as well. So anyway, Janelle, grab your seat. So yeah, this training is not my initiative, but it's initiative of Michael as our new manager. So he wants everybody to be aware. Like people only, like in our group anyway, if you are in breaker, most of the people just focus on breaker. If you do some transformer, you focus on transformer. But on relays, everything is connected. The relay makes the breaker works to do his job, trip it, and also it protects the cable and everything. So we can see how all of these services that we provide is interconnected to each other. So we'll give you a bigger picture. So yeah, discussion overview, for the relays. Of course, to avoid damage to this equipment and unit under test. Like for example, if you do testing, instead of doing more harm, you need to be aware of how you do this testing, not only for the relays, for the client, but the test equipment as well. As Steve speak to me yesterday, I think the double is sent to a service center. It cost him 30 grand, and found that there's wet spot inside. So I'm not sure how they did it on site. But if we're not, if we don't have some kind of responsibility in this equipment, it costs the company more. So anyway, we discussed about faults, relays, instrument transformer, correlation of drawing, very important. How to read a single line, schematic, DC and AC, other types of protection relays, coordination of relays, creation of test plan, of course, that's the last part, and also hands-on relay testing using Omicron test plan, because currently we only have Omicron in the workshop, but probably later we'll do the double. So anyway, to carry on, electric power industry. So some people say that relay testing is simple. But if you look at the coverage, you have secondary customer, which most likely we are involved anyway. And if you look at this primary customer, so mostly we are on power utilization. So the whole electrical industry, if you look at it, it will start with generating electricity or the generation plant. That's power generation. And you have the transmission lines, and you have the distribution. And we are here. We are practicing somewhere here. We do maintenance as a power utilization. It means that we utilize the power that was produced by power plant. So the relay and protection relay on this area, we are mostly familiar with it. But if you talk about transmission line and power generation station protection relay, that's a different kind of animal. So you don't treat supposed to be the relay as a common relay. Every industry has its own kind of protection. Probably here I can share more of you, but when it comes to power generation, I have minimal experience on that one, which is a different industry. So it's impossible to cover everything. Okay, so that's the view. So you see the level of voltage over there, 138, 750. So here, of course, low voltage step up there. This transmission line could travel probably 300 or 500 kilometers. And then there's a voltage drop here, your receiving end voltage. So the transformer here will be step up again in the ideal requirements for BHP or Rio Tinto, So that's how it works. That's how it works. So you manage everything based on your parameters. Measurement is very important because if you don't have proper instrument to measure and decide, how can you tell that you need to step up this in the proper voltage that you want for utilization of power? Anyway, the purpose of protective relaying is to protect the personnel, of course, and also protect the expensive equipment. That's like Steve Julie told yesterday. For the double, it cost him 30 grand just to fix everything because of those negligence. And also avoid longer downtime due to the repair and replacement of damaged equipment. Of course, if the relay doesn't work properly and it blown up the switchboard or transformer, that's a very big downtime for the production. And also isolate fault to the smallest affected area, which means your relay should be properly coordinated. If you have a trip in the feeder downstream, it should not trip the main incomer on top. So relay operations. Relay operation is anyway. As we continue, you can probably ask questions so that we can have some dynamic discussion. So relay operation is, of course, it designed to trip during fault, trip during overload, and also trip during over and under voltage, trip during over and under frequency, mostly cover on that parameters. And also, it behaves that it don't trip during inrush current because that's not really a real trip. The relay should understand that. Number 6, don't trip during cold load restoration. Don't trip during normal operating condition, which is very, very important. If you never have a proper setting, it might trip that one in a normal condition, which is not good. So how do the relay recognize the fault? So those things you need to put in your mind as well, but because I understand that everybody is not in the same, we have earthing, we have breakers, we have electrician, we have engineers. But anyway, I will try to explain it in a layman's term as much as possible. So how do the relay recognize fault? So, of course, abnormal current. It means abnormal current is above the rating, that the flow of current on the cable is above on the rating of the equipment. So the settings of the relay should be within the capacity or power capacity of a specific equipment that you want to be protected. Abnormal voltage. Of course, every equipment that we have, even the motor, VSD, it has a voltage tolerance. Like, for example, capacitor. You see some kind of plus or minus 20 or 15%. Otherwise, if you have over voltage in capacitor, it will be blown up inside and you see some kind of protruding body of capacitor bank. So your settings will be within the parameters requirements of the specific equipment that you want to get protected. Frequency as well, very important. All the equipment that we have in Australia, mostly 50 hertz. So above than that, it will cause some problem like overheating, or even the machines will, motors, if you put 60 hertz there, there's a lot of vibration because the frequency is different, and combination of the above. So voltage, current, frequency, mostly those things are we need to consider during testing. Now, how do we test this one? So the overcurrent trip curve, it came from IEC 60255. We should have that one. That's what I've said before. We should put that in our test sheets. And there are two kinds of curves. Sometimes we get some kind of mix up, But the IEC says TMS, or time multiplier settings. That's the one that sometimes mentioned in the relay settings. What is the TMS? But if the relay says the time dial is this, it means he's using IEEE standard. The TMS1 is IEC. So you see both sides. The IEC one is standard inverse. There are 4 up to long inverse. That IEEE, you have 3. So that's the curve came from. And if you look at this, the IEC, mostly that's the TMS here. That's normally you get on the relay settings. The duration of time will base on this and also based on your overloads. So you have the constant and everything, you can get that one here. So if you pick this one, just put this constant here. As a formula, K will be there, your alpha will be there, and your TMS from the relay. You can check now the time, your expected time when you inject the current, depends how many percent. And the IEEE is the same. You have all the constant over here, but most of the time we're using some formulated Excel. So, but that's where this thing came from. So all the constant as well, and you have the time dial from the relays. So those are two. Sometimes different relays, they prepare to use different standard, but the purpose of that is to properly coordinate the trip of the relay. If you want this to trip first, you pick the right curve. If you want this to trip the last one as your last point of defense, which is the incomer, you don't want to trip the incomer first, isn't it? Because it will trip the whole production. So anyway, what does the fault look like on the relay? As a relay tester, you need to know some rationalizing what is happening inside the relay. It should be in your head. Anyway, if you do the relay testing, it should be, you need to get around in it. So if you look at this current ABC, the voltage ABC as well. So if you have a higher voltage, you have a smaller current, vice versa. If you go to the low voltage, you have higher current. That's why you have big cables. You see those breakers, 3,500, 4,000, because in low voltage. So you see the voltage here, higher voltage, low current. But let's say you have a fault in phase A. The balance current will not balance anymore once you incept the fault. The fault will be spike up, and of course the voltage on that specific phase will be affected as well. So on the relay protection, that's what you want to know. What is my available fault on that specific part of the breaker? That's why you see different KA, different settings, and also the disturbance of the voltage will be picked up by the relay. So any idea how we can pick this up? How we can feed this huge amount of magnitude to the relay? What is the only way we can pick that up? Yeah, VT, CT. We do CT analyzer, you know. That's why testing the VT, you cannot say that a simple test, because without the VT, the relay will not work properly. Because the protection relay is only relying on those parameters that you want to feed to him. Like for example, if I'm involved in the design before in the Philippines, some people never understand that there is a difference between the protection CT and the metering CT. Once you install the metering CT on the application of protection, it will not work properly, because it will not measure this kind of current, which is thousands of amps or times 5 or times 6 of the rating, because it's only designed to measure accuracy in the low magnitude. But the protection CT is different. That's why doing the knee point is very important for you to determine if it is protection or it is a metering CT, because it's designed to measure accuracy at very high magnitude of current, which the metering CT cannot do. Same in the VT. You need a specific accurate current voltage measurement in secondary as well. That's why your turns ratio is very important as well, because that's the one, the secondary voltage, that's the one will be fed to the relay for the relay to work properly. Any questions? Okay, we proceed. Now, typical fault. You see the single line to ground, which is one line and to earth, probably breakdown of insulation or post insulator in the pole, or two line to ground, some kind of, you drop some kind of metal over there, and then it break down to ground, and the rest, the other one is three phase. It means you shorten or bridge the three phase line. So that's the kind of fault that typically we see on that part of the industry that we discussed earlier. So causes of fault, grounded cables is that's why I said earlier that this presentation is to consolidate all the services that we do. The breaker tester is not simple because we need that very accurate opening time and tripping time in order for the relay to address the fault, to clear the fault as quick as it can during grounding the cables. So cable testing is very important as well. If you don't have properly earth there, the relay will not pick up the right fault current because your resistance is too high. So by Ohm's law, if your resistance is high, your fault current is not enough to reach the specific setting of the relays. Trees, of course, if there is typhoon in some kind of tropical country, that's the problem that we have there. Poor workmanship for the splicing. Sometimes we do PD and everything, BLF for the new installation. Termination problem as well. Poor workmanship probably, or because exposed to the weather. So that's mostly the common one on the existing installation or after we energize all the installation that we have. So that's why we came there to provide them the specific data or test results. Now, line to earth fault. So of course the source. You have the source here. You have substation. You have feeder 1. If you have fault here, this feeder should not be affected because it will return there through neutral. So it's some kind of loop. That's why if your earth is not really good, you will not reach the specific setting of the fault. That's why sometimes your relay will not really pick up on the expected trip that you want. That's why when we do maintenance, sometimes the scope of work says earth continuity, loop impedance, fault of potential, because if you have fault on the field, the only way that that one can be received by the relay is a better lower resistance, like below 0.5, and also the impedance should be very low as well for you to reach the specific fault. That's why we check that one. It doesn't mean that we come there because I'm doing only earth testing, so I don't care about the rest, but all the services that we do is consolidated to each other. That's why we fail if that one doesn't meet the requirements, and we pass it if that one is past the requirements of the standard. Scary, you never ask any question, eh? Yeah. Anyway, this is sometimes not common in the industry that we have. As what I've said to those people who never came earlier, we have the industry of power distribution, transmission, power utilization. We are on power utilization. But this one is, let's say in a power plant, you generate two sources of power from the generator. Normally they have parallel generator. So you should have a better earth continuity as well to receive that specific fault. Of course, the fault will always go back to its source by theory. That's why we have neutral, we have earthing grid and everything. The system will always fault going back to the source of the fault. So if you have very big capacity, expect a very high fault magnitude as well. Of course, if you have a small transformer, it will generate more fault. Anyway, what is protection relay? As what we said earlier, continuously monitoring the power system, day and night. No load or no load, the relay should be there. Another one is send signal to trip the circuit breaker recloser during abnormal conditions. That's why if you're a breaker technician, you're looking at the speed of your opening time, the speed of your closing time, if your closing coil is okay or what. So all of this stuff, because that speed of clearing the fault, speed by the breaker, let's say opening, let's say 50 milliseconds or 30 milliseconds, you have to add that to the specific speed of the relay, how the relay process the algorithm of fault internally will add up together. So let's say average of 75 milliseconds to clear the fault. That's very quick. I think that's the standard today, which is ideal anyway. So that's why we're always dealing with time. The accuracy of that is required for us to meet the requirements of how the protection relay protect the system. Now, construction type of relay. I think for the new generation like you guys, you normally never encounter this kind of relay. But in 2002, when I began on this industry, most of the relay that I do is this, because most of the relay that we maintain during 2000 is the design from the 80s and early 90s. So it's really Jurassic. So we don't have the fancy software before. We just rely on our theory and how it works. So it's electromagnetic induction. Once you feed that with small current, the disc will rotate, and you see this instantaneous coil will initiate if you have a bigger current, quicker to react. And you have this slower coil that's slower to react as well to trigger the trip. And you have the tap. In our time today, you just type what tap do you want. But here you need to move this bolt here. You need to move if you want to tap to the smaller tap, 3.2, 3.5. By the way, the common CT that we use on those days is 500:5, 200:5. All the secondary amps is 5 amps. In our time today, common is 1 amps because of the advancement of the technology. Now, this is the new generations of relay. So, microprocessor based, it is a relay that are computer based and programmable logic. No need for you to move those bolts and nuts to put it on a desired tap that you want. And of course, the speed of the contact tripping can be programmed as well. So the logic dictates how the relay will perform its main duty of protecting the electrical system. So you can put all your logic or AND gates, OR gates, how you can put them together, and you have already the mimic bus showing the current and the voltage of different buses. That's what we're gonna do. Anyway, what is the protective zone in power system? I'm sorry, it's very technical, but just ask. We will explain as much as we can. Junel or the rest over here, Gianni. So we will talk about it. So a protective zone is a separate zone that is established around each system. You can see those dotted lines. So it has its own protection. The significance of such a protective zone is that any fault occurring within cause of tripping of relays which causes operating of all the circuit breakers within the zone. Like for example, this busbar protective zone. This busbar protective zone doesn't care about the fault of overcurrent, doesn't care about the fault on the transformer. He is only caring about this bus. Once there is any fault in that bus, this bus protective zone will trip all 5 breakers, or doesn't matter, 20 breakers, or I think the last one that we did, I think that's the rule of thumb. We did FMG Solomon, and is that a port. So there is a bus protection relay that, in fact, Lionel and myself did the pre-commissioning on that one. So once there is a bus tie, let's imagine that this one have another 1 set here, but there's a bus tie. So there is a logic. If the bus tie is open and there is a bus strip over here, it doesn't trip the other bus. If the bus tie is closed, there's some kind of inputs to the bus differential that it will trip the bus A and bus B. So something like that. So there's a lot of logic scheme that I think in our days today is very flexible. But that's the zone protection of the power system. In the generator, it has its own zone. It doesn't care to the other protection, to the transformer. It's only care about the protection of the generator, which is a different animal of protection relay. And if you have here, you're looking at the transmission line, you have line differential, all this stuff. And here again on the low voltage. If you look at them, everything is covered. That's how they design it. There's no dead zone. There's some redundant of overlapping of protections for them to cover if in case there is some kind of problem, or sometimes they do some redundancy of protection for them to, like for this one, this breaker is capable of tripping through signal from bus differential if there is a bus short or fault. It's also capable of tripping through overcurrent on this zone. So you see the overlapping over there. That's why setting is very important. Any question? So that's the industry that we are normally doing the maintenance. So what is the protective zone in power system? So there is a closed zone protection, which is the differential. It doesn't care about the overcurrent. It only care about the internal fault of the transformer. That is the closed zone protection. When you say open zone protection, it means that 5051 will cover the rest going downstream. It's not only specific on this one, but cover whatever fault downstream. If that one doesn't pick up downstream, this is the line, the last line of defense that you have. So there are two kinds of protective zone.
And those two kinds of protective zones can be on one relay?
Can.
Can.
Can. So most of the relays now is multifunction. Multifunction. Unlike those days, one door is full of relays. In my time, it's just ridiculous. But now, because of the advancement of technology, the relay can be reprogrammed depending on the application. Okay? So yeah, different kind of zone. If you look at line differential, yes, that's closed zone because it's only looking about the differential. Transformer differential, closed zone as well. Bus differential is closed zone as well. Just to give you an idea how to identify this specific protection. What about the REF? Everybody encountered this. Closed zone or open? REF is restricted earth fault.
It's closed. It's just
Yes. It's only transformer, yes, correct. You're looking at the spot of internal fault between the line transformer going back to the neutral. High impedance differential fault, I would say closed zone as well. Because you're looking at your summation. You know that metro cell thing is always instantaneous. You notice that most of this closed zone is always instantaneous strip. Line differential is closed zone, transformer, of course feeder overcurrent or motor relay, that will be open zone because it can look to the longer cable going to the last point of energized cable anyway. There's some short there, the feeder can pick that up in some point. Now, older generation protection relay. This is what I'm saying. In my time, you see this one guy here, it's only gas turbine trip. So all these boxes that you see only work as one function. You have trip supervision. It has some kind of label there anyway. And you have reverse power. It's individual box, individual function. All of this label here is labeled on that relay. There you can find those functions. What is the work of that relay? So it's individual function. So you see the door of the panel is full of relays. But in our time, that's the new generation of relay. Those many box or relays on the door mounted, now it's only one. All the functions need to be activated and it will provide you the protection that you want. So it saves space in terms of installation, and also it gives you more flexibility. And also in wiring, you have a couple of wirings at the back compared to the old generation of relays. Now, how do we measure the fault? That's where this thing coming from. So some people ignore that, it's only CT. Don't worry about it. It's only VT. But the test result of your CT VT will be very, very important, how the relay works or how the relay do its job. The accuracy of your CT VT and also the connection. Even you have a good CT and you restore it in a wrong way, or you forgot to put the common, you forgot to open those CT link, it doesn't work. So we have to be responsible in everything that we get involved. And this is the picture. So sometimes we undo the cable in this side just to do the turns ratio. Make sure that you put it back properly and tight enough to do its work. CTVT. Yeah, now, how do we measure the fault? So that's it. Analog input, voltage current relay, digital output, close or open, signal to treat the breaker. So my mentor said there is no real time when in terms of measurement. Even though electricity travels like a speed of light, still you have some kind of delay. So if there is a fault, I can remember this 20 years ago, there's a fault here, and that one will send to the relay algorithm will process, there's a speed of computer or memory inside the relay, will determine, this is instantaneous trip or this is overcurrent trip. So that sort of process inside the relay will create some kind of, let's say, milliseconds delay in order for you to initiate the outcome like trip or no trip. And the breaker as well has its own delay. That's why you're measuring the opening time and closing time. So that's how it works. There's some kind of process or delay before everything. You can see the outcome of that specific fault in the system. Now, primary versus secondary. If you look at this drawing, simple drawing here, you have the potential transformer, which provide feed for the voltage feed to the relay, and you have the current transformer feed to the relay for the relay to process and monitor it 24/7. And if there is a normal flow of current and voltage here, this one will not activate. But if there's a fault here, measured by this one will move and will trip the breaker. That's how simple it is. This is FMG, I think. So there's a bus tie and everything. So there is some arrangement. You can see all the models of protection relay. You have CT-BT. What is the rating of CT and everything. That's how we do the takeoff in the design of the switchboard before, including what is the rating that we want to order from GE, and also the size of the CT-BT. So we fill this out based on the design of the client. So anyway, CT-Link. So CT-Link, that's what I mentioned earlier, that this is where we do our testing. So we put our banana plug here and inject it to the relay. So sometimes people forgot to restore it properly, and you will have an open circuit relay. And if the switchboard is energized, there will be a high voltage, induced voltage on this area because you open the CT. and you will end up burning this and burning the CT as well. So this one should be restored properly. That's why we normally take photo as found and as left, so that we can make sure that everything is restored properly. An open CT will cause high voltage, high induced voltage in the secondary. So that is the representation of the single line. So this is from the CT, and this side will go to the relay. And mostly you can see this on the drawing like this. So this is your protection relay, and this is your voltage. Of course, you have to fade that from the VT going here, and you have the CT going here. So if you do test the relay, make sure that the VT is isolated. Because if that one is closed and the encomer is energized, you still have a VT voltage here. And you connect your test equipment over there, it will bugger the test equipment. Another 30 grand, according to Steve. So we have to be careful, especially if we're looking on the schematic, make sure that we're looking at the right schematic. So on the VT, you have to open that. And on the CT, make sure that you injected on the right specific CT link. So normally, sometimes the rest, the experienced guy, Janelle, and the rest of the guys here, sometimes if there is no drawing, we only look at the terminal numbers. Because from terminal number here, C11, we can trace that back on the CT link as C11. That's where I'm going to connect my red phase. White, red, white, blue. So normally we can identify it, but it's better as well to have the proper drawing as much as we can. Okay, and also we're looking at the trip coil. So the trip signal of this relay will go somewhere here. That's where we're gonna monitor our trip time.
Sorry, Francis. For the CT link, we usually don't do live online work. But let's say the client is happy that they don't want to turn off the CT's current, and if we wanted to use, my point is, let's say if you wanted to do live testing of the relay, what's the procedure to handle the CT?
I think I would say no. As much as we have to do some isolation.
Okay.
Yeah, because if, for example, the big risk on that one, like for example, if this one is closed, energized, and they said, oh, the motor is off, don't worry about it. So you test the motor relay because the load is off. But the thing is, okay, you isolate this one, you short that one to make sure that there will be no backfeed here. You short your CT link, and you test the relay. In some point of duration of your testing, in where you disable this, you remove this for testing, you isolate it, something happened on the cable. You don't know. The cable will run how many longs out there, and you have line to earth fault, and what will happen? This one will not open. The fault will go upstairs and upstream, and it will trip the whole plant. That's another thing. And if this one is open here, you're doing testing, there will be a induced voltage here, high voltage. You will get accident because the relay, the CT will produce some induced voltage if you have current flowing on the primary. So still, we suggest that we have to do proper isolation. Yeah. That's the safest one. That's sometimes some of the site supervisor don't understand. But we as a specialist, like doing this kind of job, we have to explain to them properly the way we understand the power system.
And also, just an add there, just to cover our company in any happening like unwanted trip on the system. So at least we inform them that this will be the scenario.
Yeah.
If we're doing this kind of testing. It happened many times to me on site. One of the gold mine, somewhere in between Newman and Kurt. The guy, I don't know if he's an engineer or Sparky. He always tell me that he always do this.
Yeah.
And then I said no, I don't want to do it. I need to call my boss before before my next step, right? And then what happened there is he just started without any any he didn't inform me that he already started disconnecting. And then once he disconnected cable, tripped the board.
So if that one trips, the whole production is affected.
Yeah. So I cover GKS that time. The second one is the worst one there is the second time was he tripped the whole underground power. So which is very dangerous as well because you switch off the extraction vent which gives fresh air underground. So it's fault again. I think that guy is stuck after that.
Yeah. So that's the scenario.
Yeah.
In the production, sometimes hours equivalent to money.
Yeah.
Like utility, if you trip one substation covering the whole suburb of Canning Vale, that hours of downtime will cost you money because we're talking about millions here of power, delivered to the industrial site and also consumers. So we have to avoid that. If they insist, we have to explain to them. Ask Michael, inform him this is the scenario and everything, and then it's their call. We inform them. Yeah. Any question?
Yeah.
So yeah, that's mostly we're looking as a relay tester, but everything is interconnected in terms of what we do in a power system.
I just want to add something in that drawing as well, because most of the time, young engineer just do connection testing without analyzing the drawing and the scheme. Sometimes we always forget the breaker failure.
Yeah.
Especially when we're doing in camera. The breaker failure is very risky when we're doing relay testing because the relay also will send signal upstream, which sometimes cause a big issue. It will drop the whole supply in that particular account. So we must always put in our mind, especially on the protection engineer, that breaker failure, we don't forget the breaker failure.
Yeah. So breaker failure means if you have an instantaneous trip and there is no signal coming from the breaker that it already trips the breaker, the relay looks like the coil is failed. So I need to do something to cut off the power upstream because the relay is waiting for the breaker to feed him some inputs. Hey, man, I'm already tripped. You're right. Don't work as a breaker failure. So if you never disable that and you continue injecting like overcurrent, instantaneous, and the relay will think, looks like there's something wrong with the breaker. I need to activate this. There is some kind of process of logic internally on the relay.
Is that an actual internal setting in the relay that can be activated and deactivated?
Yeah, you can activate, deactivate.
So, from what I'm hearing there is when you're testing a relay, you should deactivate the circuit breaker down the setting and then reactivate it when you're done.
Yeah.
Or the best way to do it, remove the contact.
Yeah.
So
And when you reinstate that one, you must ensure that that one is no voltage or it's open circuit.
So which would that be in the case of this drawing? Does this one have the breaker failure contact in the drawing?
So at the moment, this one doesn't have the breaker failure because it's looks like a feeder.
Yeah.
So normally they add some points here saying
Yeah.
trip inter-trip
Yeah.
to upstream.
Yeah, and there'll be a separate line.
Yeah,
Separate
somewhere,
lines,
yeah.
somewhere in there, yeah.
Your breaker failure, is that always normally open or can it be normally closed also?
Depends on the
Sure.
drawings and the application of the contacts, yeah.
I remember Calcrash, we did that on Hope Done 4, right?
That was intertrip.
Intertrip, okay.
Yeah. And also the intertrip, yeah.
Yeah, intertrip, we have to
As
be
well.
careful of the intertrip.
Because intertrip also can cause some big issues.
Yeah, it happened to us in HD4, and then I think from West Angeles, all the engineers rush going to HD4. And then looking who is the one who tripped our line. And we don't know that there is some kind of intertrip like that there.
That supervision relay you're talking about, is that an old thing now?
Intertrip is.
No, it's still applicable. Yeah,
Is that one relay sending a signal to the supervision relay and that trips the breaker?
it monitors the coil,
It is maintained by.
the trip supervision, trip circuit supervision. So it also monitor the coil. Like if your breaker is open, it's trying to monitor the closing coil. If the closing coil is healthy, there is some kind of a continuity over all the drop voltage is drop anyway. So it will allow you to close the breaker. If that one is not healthy or some reason that you pull out that specific terminal, monitoring that specific closing coil, it won't allow you to close the breaker. Sometimes we're having hard time, why this one doesn't close?
It will inhibit you to operate the breaker
Yeah.
because it's not safe to close the breaker
Yeah,
if your trip circuit is unhealthy.
yeah. So something it's a specific circuit. Normally they have schematic over there monitoring this coil. I think this is the trip coil TC.
TCS, normally they call it
That's the one.
TCS,
Yeah,
trip coil supervision.
yeah,
So normally they connect that one in one of the inputs of the breaker, particular inputs, just to monitor.
yeah.
Yeah.
So that's the input for your relay, isn't it?
Yes.
So that's inject some sort of small voltage or current
Yeah.
to check the healthiness.
Yeah. Normally, the input voltage, the input of that relay monitor voltage. But some of the design they use mechanical supervision. You know the
Switch, rotary switch.
different supervision. It's like a mechanical type, but
Almost
also
like a position
Position, like a
slice.
so it depends on the application again. So it's very wide. Protection is very wide.
Yeah,
It's not straightforward.
it's not straightforward.
Yeah.
That's a good one. Now, so we run through all of this safety precaution.
Yeah.
So keep in mind, should be
Yeah.
properly ready for testing. So by looking at those
Yeah.
scenario,
And another one as well is not only looking on the hardwire, because protection nowadays the relay also can talk through communication.
communication.
So we can't see that one just looking on the drawing. We need to study the logic or they call it small PLC inside the relay. So hardware is different from the software. So that's also we always forgot, like looking on the logic settings of the relay.
Can you do that from the front, or do you need
No,
software?
software.
Yeah.
That's why familiarization plus know how to understand the PLC or logic inside the relay. Because I have another example when I did
I think that one is
a
Northern Territory.
Northern Territory.
Yeah,
I spoke already to the because what happened was they forgot to add an additional inhibit to test the relay. So when the breaker is wrapped in, so there's a particular logic they're saying the virtual output. So this is the one that we cannot see, the virtual output, because virtual output is more on addressing like one is partner to number 23. So that number 23 might be the incumbent. So we cannot see that one, but if you have proper knowledge on that, so you will assess that this one, if you do any testing on that particular relay, it will treat the incumbent via communication. So what was happening was, even though the breaker is wrapped out, they didn't put any supervision that the breaker is wrapped out to disable the function.
Yeah.
So what? And they didn't believe me again. Like, no, it's already done in commissioning. But I need to get your permission if there's something wrong. So that's why documentation is very important. Even though it takes a while to do relay testing. It's not like breaker that you just connect your cable, that's it. Relay testing needs to be, you have a good experience and knowledge on what you're doing. So I get that permission again to the client. So this kind of analyzing is just to cover yourself. Because we are the one who, if we did something wrong, and then we are the one who suffers, isn't it? So I said, you need to sign on my JHA, this and that, and then what? I just doing. I'm not starting my testing. I just doing metering check only, and then switch the income.
Yeah.
Yeah.
So that's the thing. Yeah, I remember the job. I sent Junel there. I grabbed all the schematic and I discussed with Junel. That looks like a simple one, but in my part, I didn't see that one as well because that one is internally on the relay. So anyway, it's a familiarization. You know, if you really get your head around it, it's a totally different world. Yeah. Anyway, yeah, that's good discussion, and I want to show you some kind of failure here. I don't know if I can click this one here. Oh.
Yeah, I think.
Can we put that in there? Probably we minimize that. Oh, that went to, yeah, that one.
Maybe
Minimize that one. Yeah, so this one will show you the failure that will cause if there's some kind of malfunction on one of the specific component to isolate the system.
that's all.
Yeah, that's the one. So this is one of the substation. I think it's a possible failure. That's a transformer. So there's a fault, and the fault never clear for some reason, and the oil come out, and the oil reach the flash point. They call this flash point, and it just vaporize the thing. So you see, and then probably if you can think about what kind of failure, if you are the one who will analyze it, what kind of failure do you think the one? Anything as what we have discussed.
short circuits,
And
many things will work in there. Glucose will work, your oil temperature, winding temperature trips, nothing work, isn't it? If those inputs went to your relay, probably a relay didn't give a supply output to your breaker, and if the relay give an output to your breaker, probably breaker didn't work.
Oh yeah,
Maybe the breaker
And
is fake.
the interface didn't work.
yeah.
Correct.
So,
So-
many things are.
It could be, yeah, you're right. It could be the relay is working properly, but when the relay tried to send trip signal to the trip coil, the trip coil doesn't react to open the circuit. That could
What's
be,
the options people as well?
yeah, or the breaker is working properly and the relay doesn't get the proper signal
Yeah.
for the relay to determine that I need to cut off the system for some reason.
Yeah.
Yeah. So everything is interconnected. Your CT should be properly connected to the relay to give the relay the right information. Your breaker as well, properly tested. That's why we do maintenance with that one. And the relay. So everything is just working together, giving you the whole picture of what we're doing.
Might be the city is shorted.
Yeah, it might be the city we live in bridge because of testing. So there you go. Investigation will come in. Oops, who did the relay? You know, they bridged the city link. So those kind of simple thing that we forgot on the city link will cause a catastrophic
Very.
problem. Yeah. So what time is it? I think we are almost quarter. But if you want to have some break, yeah. Eh?
can also be a screwdriver.
Yeah. Anyway, yeah, if you want to clear this, let me know. So yeah, that's it. Simple thing. We forgot, but it will cause a big, effect to what we do. So anyway, accountability involves in relay testing, test engineers. We know that the electrical industry is really small. Everybody see each other on site. Can you imagine if you did some kind of thing like that, negligence? They will on production losses. So it's free to ask. We are team here. If I don't know, then I ask. I ask Kalpesh. I ask Dane or Christian, because sometimes we are too much focused in one area. We forget something. Okay, we are team. Okay, so overcurrent air fault. This is some kind of. I can probably try to explain this as much as I can in a layman's term. It's a bit technical, but just giving you some kind of overview of how the current flow. The protection current transformer is current transformer like ratio, polarity, as what I've said, class, if it is protection class or metering class, the knee point, the one that we saw in CT analyzer. So this is the older generation of CT secondary is 5 amps. So of course, if 400 amps is flowing to the line, the secondary automatically 5. If this is 200 amps, the secondary will be half as well, 2.5 amps. So that's a simple ratio and proportion. So you see the overcurrent and earth fault. So composed of 3-phase CT, overcurrent elements and earth fault elements. So you have that there. This is your overcurrent, red, white, blue, or ABC, and any stray current will be picked up by your earth fault coil. This is, you have to look at this as your protection relay terminals. This is your CT link, earth, and everything. So if we go there, so on the 3-phase system, we normally have 120 electrical degrees apart from A, B, C. For Y, delta is the same. And if you maintain that angle, you will have no current flowing here. So like, for example, you have balance red, white, blue, 5 amps, 5 amps, all will be looped in this area because you have maintained 3-phase angle over there. Just to give you some kind of idea. Sometimes when you test the relay, you have to rationalize the flow of current in your mind. Like for you to understand what is happening inside the relay. So you have balance current ABC, you see the waveform. So one cycle here, one cycle, so you end up somewhere here, the one cycle is 0, so you have 20 milliseconds. So that is one cycle, okay? So once you maintain that distances between these three magnitude, 120 electrical degrees, you will have a balanced system. So like for this one, even though I have an unbalanced circuit, 50, half of that here, half of that here, since I have a balanced angle, there will be no flow of current here. So that one will go loop to each other. This 2.5 will sum up and will come up 5 amps here. So and so on. So, so that's how it goes. The angle is very important. Now, and the primary side is the same. So 50 amps, 25, 25. So same, there will be no flow of current on the coil of the earth fault because your angle is affected. Now, what if you have a single phase fault? Now it's not balanced anymore, isn't it? Because you have fault here. So because of the angle is pulling to each other, opposite to each other, there will be no stray current on the neutral. So still you don't have flow of current on the earth fault because the two opposing current will cancel out on this loop, on this area here. So there will be no earth fault happening because you see this behavior here, the opposite to each other, 180 degrees. That's like you have a thongs, the clamp meter. You have a single phase load. You clamp that two together, 0, because they're opposing to each other. It's a single phase load. But if you separate them and you clamp only one leg of that single phase load, you get some reading because they're not opposing to each other like this or like this. Yeah, hopefully it's a bit clear, but that's how it goes. So single phase fault, it always pick up single phase or phase over current or phase instantaneous, but not earth fault. So that's the behavior of a single phase fault. So they are opposite to each other, 180 electrical degrees. So this one and this one cancel out. So your earth fault will be 0 because they just cancel out each other. That's how it goes. So there will be no earth fault flowing. Now, earth fault. This is now the scenario of earth fault. Only one phase. If you inject single phase on the relay, it will see it as an earth fault because there will be no other opposing current in other leg. So if you go here, it will go here on this coil and go back here. So it will treat that as an earth fault, which is it will go first because this is instantaneous strip. Depends on the magnitude. There's an instantaneous strip as well on the phase A, but most of the time this one will go first. So there is only a single one. That's the time that the earth fault will work because of the flow or the behavior of current. So that's the secondary one. So the way we test the relay is based on the understanding that we have on the power system, like this one. So if I want to test the earth fault on the specific relay, of course, I use my double or Omicron. I can inject here straight away because I only need this. If I'm gonna do, I can do it here because it's loop anyway. If I do it here, you have a neutral going back here. It's the same thing. So there's so many ways to skin the kangaroo, but if you understand the system, you need to know how the relay reacts and how you attack the specific protection that you want to do. So proper understanding of the system is important, and also the software of the relay is familiarization. I'm not really familiar with heaps of different relay, but the important thing is we understand how the system behaves.
Because if you know the basic principles, even though you're doing cell, iPhone, any brand of relay, they following the same principles.
Yeah.
So you can't miss out this kind of setup. Yeah.
Yeah. So there's another way as well. Like the saying, if some people, okay, this one's creating problem. I want to trip this, but this one creating problem. Since you have access on your laptop, I will disable that earth fault for the time being and inject without changing my connection on the relay. So that's the time that I can test this over current. So if I enable this one, that's the time I can test as well the earth fault because this one will trip first. So there are so many things that it's up to you how you understand the system and how you understand the software.
You can also click this one, so you can also inject on two phases with opposite direction.
Yeah.
Because as Francis already discussed on the previous one, if it opposes two
That one.
two directions, so it will cancel out.
That's why when you see on the test results, sometimes we have overcurrent phase A, B,
B. Yeah.
because we need to avoid tripping this guy. So we do the combination of A, B, B, C,
Yeah.
C, A.
Just to trick
Just to trick the relay.
the relay.
If you don't want to disable this.
So you don't disable the earth fault from the relay.
No.
So you just change the connections on the Omicron.
Yeah.
So
Not change the connection. Just inject
Inject.
Get
opposite
180 apart.
180 apart.
okay, so let's say I'm just trying to understand. So let's say I want to do A to B. So I'll put my red lead on A and my neutral lead on B.
No, that's
No.
neutral. So you don't need to change any
Connection
setup.
is the same. Connection.
Okay, connection.
Connection.
Oh, it's just the angle from the software. Okay.
Correct. Yeah.
You have to meet this one here, the earlier one, 180
That's
degrees. So you see this, we'll show you because after this, we're gonna do some kind of test plan. Some kind of test plan. I think we need to do some kind of break, I think, because when we go to test plan, it will consume
Yeah. more-
another time.
Yeah.
I show you how the step by step of using the test plan. And then after that, I already told Michael that it's better to spend a time in doing the test plan. If you want to get use of the test plan, we will set up the relay and I will show you how to generate the test plan, but you have your own laptop, input all the information there on the test plan, and since the Omicron and the relay is set up, if you want to try or practice if your test plan is working, you plug it in there. After you finish to create your test plan. Okay?
That's great.
So I think that's the best way. If not work, then troubleshoot.
Yeah.
We'll show you how to troubleshoot. But here, we'll show you how to start generating the test plan before we go back there to set up everything. So I think we have to do some break. Is that?
Can you just close the front door back?
Yes, right. Save it probably.